For the second part of the seminar, we will go more in detail about FPA chemical imaging. So when we use this array of detectors instead of using a single one, which is the best configuration to do chemical imaging. And we will go through some important part of it. After that, we will see like a few examples of application of FTIR chemical mapping. And then finally, I will just give you like my opinion about the use of this technique in a topic related to urban drainage, so the analysis of microplastics in urban waters. So when we talk about focal plane array imaging or FPA imaging, we have to remember that basically we have a detector that is a sort of chip that is including many hundreds of thousands of individual detectors. Each of these detectors can measure like an infrared spectrum. So basically we can collect a lot of infrared spectra at the same time over a wide area of a sample. We basically have a sort of infrared camera connected to our instrument. The first model or first instrument was introduced in 1995 and was called Stingray because originally these FPAs, they were basically a component of the guiding system of the Stingray missiles. So it was actually very difficult to obtain an instrument with this configuration because, of course, the US government was monitoring who was getting this and for which reason. So not everybody was allowed to have an FPA, FTIR back in the days, but nowadays it's basically a free technology. When we talk about FPA, we have to introduce the concept of tile and mosaic imaging. So every focal plane array, so every picture we collect with this array of detector is called a tile. Okay, so imagine that this is our detector and we take several thousands of spectra at the same time. But then we can also measure many tiles and stitch them together to create a mosaic image of a bigger area. In this case, we have 4 × 6 mosaic tiles. So we of a detector that has like 64 by 64 individual detectors in one of each tiles, and basically we collected 98,000 spectra in our acquisition on an area of 2.2 × 1.4 millimeter. So with the FPA imaging, we can collect infrared images of large areas. For example, this is one of the targets that are used for the stage calibration of the instrument. A quite detailed image in a quite large area. But how detailed are these images? To know that, we need to introduce the concept of pixel resolution, the pixel size, and spatial resolution. So we know that the resolution is governed by the Rayleigh criteria, and it's basically 0.61 lambda over the numerical aperture. And the pixel size at the sample plane, so where we have the sample, depends on the size of our focal plane array detector and how it is projected onto the sample. So the pixel resolution, the total system magnification, is a function of the objective and the intermediate optics we have in our system. If we try to give an example on how to calculate the pixel size in our system, we need to have this information, the field of view, so it's based on our objective, and then we need to know the number of pixels on our detector. So for example, if we have a detector that has 128 × 128 pixels, to know the pixel size, we need to divide the field of view of a specific objective, that in this case is 704, divided by 128 pixels, and then we will have a pixel size of our system of 5.5 micrometer. So we will be able to collect spectral information every 5.5 micrometer. When we also do imaging, we need to know about spatial resolution. So the ability to detect the presence of two objects next to one another, and the distance between those objects is given by the Rayleigh criteria. Again, the same formula, which is translated finally in this 0.61 multiplied by the wavelength and divided by the numerical aperture, which is related to the objective that we use. If the numerical aperture of our objective in this formula, basically we can have that the theoretical spatial resolution is dependent on the wavelength. Here on the right side of the slide, we see that, I mean, if we have like a low resolution, we cannot distinguish between two objects. If our resolution is still low, but not that low, we can start to distinguish these two objects. When we are at the Rayleigh, basically our resolution is exactly 0.61 over the numerical aperture, and then when this is greater than 0.61 lambda over a numerical aperture, we can clearly resolve two objects. An example of the spatial resolution is on this like two chemical maps I'm showing. As you can see, they are the same chemical map, but on the first one, which is this, we are visualizing this polystyrene and on a polystyrene beads, the red part, by collecting or isolating the signal at 3000 centimeters -1. In this case, we have a resolution of 3.3 micron. But if we image the same beads and isolate the signal from another wavelength around 1400 centimeters -1, our resolution is a bit lower or worse. So basically, the spatial resolution depends on the wavelength that we are measuring, and also the wavelength we are using for the imaging. So higher spatial resolution will occur at shorter wavelengths, which in FTIR occurs at high wave numbers. So better resolution at high wave numbers, lower resolution at low wave numbers. To summarize about spatial resolution, what we have to remember that, I mean, when we have lower magnification in our system, so we use lower magnification objectives, we have a lower pixel resolution, which will translate also into lower spatial resolution according to the wavelength, as we just saw. But we will have a larger field of view on this using the same detector. These lower magnification analyses are suitable for low resolution imaging of large areas because it's faster. Like, for example, in this case, we can image the whole calibration target with a low resolution and low magnification object, a 4 magnification infrared object. On the other hand, when we use high magnification in our system, we have a better pixel resolution, a better spatial resolution, but we also have a smaller field of view of the sample by using the same detector. In this case, high magnification analyses are suitable for imaging of small areas where we need high resolution. We really want to see the details. So summarizing, from large areas with low magnification, in this case, this one is at 19 times 19 micrometer pixel size, we move more and more to smaller areas, increasing the resolution of our chemical imaging until we reach a resolution that can be really close to a very few micrometers. A few words about the focal plane array detector size and the related field of view. The pixel size of a specific detector remains the same regardless of the size of the detector. What changes is the field of view that you can image in one go. For example, the 128 times 128 focal plane array can collect around 700 times 700 micrometer in one single analysis. If we use a smaller detector like 64 times 64, you will need to collect 4 tiles and stitch them together to cover the same area. So basically we will have an overall speed that is 4 times lower than the bigger FPA. So to summarize, the pixel size for a given objective will be the same for different size of detectors, but what changes is the field of view, because the bigger is the detector, the bigger is the field of view. So from a 32 times 32 detector to a 64 times 64 to a 128 times 128. So the bottom line is better to have a big focal plane array if we want to image faster and to image larger areas. We can measure in Micro-FTIR-Imaging in basically 4 ways. These schematics basically show how the signal is collected in Micro-FTIR imaging, or also in single point. And also I try to highlight also the limitation regarding the sample thickness in some cases. So in the higher part of the slide, we have the acquisition mode. So we have transmission, reflectance, transflectance, and micro ATR, or attenuated total reflection. And then just below the mode, we just have for all the system, or for all the acquisition mode, a representation of our objective. As you remember, the objective in infrared microscopy is called Cassegrain, and is an objective composed by mirrors. So this is a parabolic mirror, and this is an hemispherical mirror that is looking basically the parabolic one. So the infrared light bounces to the onto the hemispherical mirror, bounce back to the parabol, and is focused on the sample. If we work in transmission, then the infrared beam will pass through the sample, and in order to be collected, there will be another objective that is placed upside down, and it's called condenser, because it will recondense the infrared beam and focus it back so that it can be collected by the detector. Analysis in transmission are very useful if we have a thin sample, but the thickness of the sample is limited to around 30 or 50 micrometer. Above this size, we start to lose information when we record our infrared spectra. If we work in reflectance, we will basically send our infrared beam onto a reflective sample, a glossy material, for example, and then recollect the partially absorbed infrared light through the same objective that will then send the infrared beam to the detector. In this case, we don't have limitation in thickness of the sample, but we need to have reflective samples, for example, a glossy material or a paint or a varnish. We can also use a kind of intermediate way, which is called transflectance, where basically the infrared beam is passing through a very thin sample, you can see 5 to 10 micron, and then is reflected by a substrate that is placed below the sample, which is typically a gold-coated slide or an infrared reflective slide. The last mode, the micro ATR, uses a sort of crystal, the ATR crystal, which touches the sample, and then a small infrared wave protrudes from the crystal into the sample. It's partially absorbed, and the beam is sent back to the objective and then the detector. In this case, we can analyze thick samples, so we don't have any thickness limitation when we use ATR FTIR. When we work with the FBA imaging, we have to deal with what are called the FBA results. It creates, FBA imaging creates a data cube that contains both spectral and also spatial information. And the file size that we obtain can become quite big. We are talking about several gigabytes, around 20 gigabytes if you have a very large area to image, and millions of spectra that you have to analyze. So it can be quite demanding and frustrating to explore big chemical maps. One way to make it easier is to use filters for imaging specific components on the spectra. As you can see, this is an optical image, and this is the raw chemical image that is not telling us that much. But if we apply specific filter in some spectral region that highlight the presence of specific, for example, molecules and therefore materials, we can isolate in the chemical image specific areas. And in this case, we have a particle that is composed by acrylic paint. By isolating this area, and therefore the map will show us where there is more intensity of this part of the spectrum. Then if we choose another part of the spectral range, we are actually highlighting another area of the map where there is another type of particle, which is then identified as polyvinyl chloride, a very common plastic material. And then finally, by highlighting a third part of the infrared spectrum or spectral range we chose, we can actually highlight another type of component, which is basically related to these fibers, which are cellulose fibers. So spectral filter or image peaks can help us to read through chemical maps. So after that, I will quickly go through the main application of the FBA micro-FTIR imaging, and which is widely used in several research areas, from biomedical science to material science and also forensic, to cultural heritage analysis, and also more and more into environmental analysis. The first example is related to a chemical image of a large sample of carcinoma tissue section. In this case, what I want to stress is that you can use the flexibility on your system by using, for example, a low magnification object to collect a large area in a quite, let's say, short time. And in this case, what has been compared was the signal of the spectra, the infrared spectra, so the chemical information in our map, by using a 4-time and a 15-time magnification objectives. And as you can see, even by using a low magnification, which give us also a lower resolution and a lower signal to noise, we can still obtain good results. So low magnification objective allows large area mapping in short time. They have a large field of view, but also on the other hand, a large pixel size, so low spatial resolution. But still, for a screening, they provide enough spectral quality to do large area mapping. The second example is more related to material science, and it can also be applied to forensic analysis, and it's the analysis of a multi-layer paint sample. Basically, with chemical imaging, we can isolate different components that are basically composing or making up our sample, as you can see in the image on the right part of the slide. And how we do it? We do it by using the image peaks or the spectral filter I briefly introduced in a couple before in a slide. So by highlighting specific part of the infrared spectrum, we can see that the presence of a specific component, and then you can clearly see that changing the part of the spectrum we highlight, we isolate also a different layer in this multi-layer. So basically, we can identify 4 layers and then distinguish them because they also have a different infrared spectrum. So how we do it? We will then run a so-called library search on the individual spectra, and if our databases are good enough, we can then have a nice outcome. For example, the layer number 4 clearly resemble polyester resin. So the feature image based on spectral peaks are unique to each layer in the 4 layer of this paint chip. The next application I wanted to briefly mention is the chemical mapping of some degradation products in cross-section from painting and painted objects, so some sort of cultural heritage related activity. In this case, it's possible to identify different components in this cross-section by again using different spectral filters. So in this case, it was possible to image this lower part of the cross section and isolate zinc carboxylate, so that are the degradation products of soap. And then in the upper part, instead, some pigments were identified, as well as the binding medium of the pigments itself. So it's a very powerful tool also when you want to identify the components in stratigraphic or cross-section samples. Another application of FPA and µFTIR imaging, it's related to microplastic analysis. In this case, we use the features of this technique to obtain spectral and spatial information simultaneously. So what and where we have our microplastic, so which type of microplastic and where it is in the sample. What do we do when we have so many particles to identify? It can be messy and time consuming. And if in a sample we have, I don't know, thousands of microplastics, it can become very difficult to go manually through the map. To solve that, when we collect several thousands of spectra in one go, we can basically compare them automatically to a reference database. And we can do that by matching each map pixel to a reference spectrum. And with that, we can create a score for this matching. And with these scores, we can create a map of scores and rebuild our particles in a two-dimensional way. So that basically from the particles that we have in our microplastic sample, we can replot the particles according to their chemical composition, and we can obtain a polymer-based map that can allow us to identify every single polymeric synthetic particle in the samples we collect and analyze. This is a typical result of a microplastic analysis by using this specific feature that we developed in Aalborg University, this software called Simple Systematic Identification of Microplastic in the Environment. As you can see, we are on the left side, we have an optical image where we filtered a sample of urban waters. In this case, it was from an outlet of a wastewater treatment plants. And then our software automatically re-image the different components that are on the sample, and it already assigned them a specific chemical identification without going through the image peak or spectral filtering that I described in a few slides before. So it's an improved tool to do semi-automated or almost fully automated chemical imaging data analysis. Besides having like a false colored map for each polymer, this software provides us information about the chemical identification of each particle, as well as the number of pixels composing the particle, and some morphological parameters such as the area on the map, the ferrette max, the ellipse minor dimension, the ferrette minor dimension, and so on. By assuming a third dimension, you can also have a rough estimation of the mass load of plastic in your sample. And this leads me to conclude also the presentation, because this seminar is somehow related also to urban drainage. And I think that microplastic is an emerging pollutant that is also somehow related to urban waters, because I mean, most of microplastic ending up in the ocean are land-based, around 80%. So it's important to monitor the magnitude of microplastic pollution in urban waters, because they are sources of microplastic to the environment. And it's possible to do it by using FPA µFTIR imaging, like for example, my colleague Fan did in stormwater ponds, where she measured the concentration and the chemical composition of the microplastics that are floating in the stormwater ponds. And also it's possible to do it in the sediments, exactly by doing the same type of analysis, so FPA imaging analysis. But also we can assess the efficiency of treatment system for microplastic pollution removal in wastewater treatment plants. In this case, another colleague of mine, Marta, assessed the efficiency of a system of disc filters to remove microplastic on a tertiary stage on a wastewater treatment plant. And finally, if we can also estimate the mass of our polymers, we can somehow make we can perform a full mass balance of the plastic that is entering, for example, a wastewater treatment plants and the one that is exiting treatment plants, like my colleague Lesse did in 2021. So we can use this analytical tool to provide really accurate and also robust data about the plastic and microplastic load that is entering the environment, but also that is like affecting urban water. So to wrap up, we discussed about FTIR spectroscopy and its basic principle. We know that it's a versatile and widely used analytical tool to chemically identify many materials. And of course, if we identify materials, it's because we can identify the molecules that are making up these materials. It's basically based on recording the molecular vibration after irradiating the sample with infrared light. And FTIR work based on the principle of the interferometer, the Michelson interferometer, which is, let's say, allowing to collect the signal in a quite short time. And then this signal can be transformed into frequencies by using Fourier transform. We can also collect information at a microscale by using an FTIR. And most of the knowledge about microscopy can be transferred to infrared microscopy. Basically what we do, we use mirrors instead of lenses, and we use a cast grain instead of a normal objective. The cast grain is the eye of the micro FTIR. We can analyze single points in our sample, but we can also perform a chemical mapping that provides us spectral and spatial information combined to give us chemical images of a sample. And this FTIR imaging can have a broad range of application because it's a versatile tool. It's used for, from material to biomedical science, and increasingly is also used in environmental analysis. And microplastic is probably one of the most prominent emerging areas where micro-FTIR imaging is used for an unbiased and accurate measurement of the microplastic load in different samples from different environmental matrices. But of course, if it's too good to be true, maybe it's not true. It's important to remember that FTIR and all the related techniques are only one of a wider array of methods and techniques that can be used for chemical identification. It's good for many things, but it's not good for everything. So beware of misinformation. And always try to dig into the literature if you are planning on using this technique for any application related to your research field. Here we have a little bit of references in case you want to go more in detail. And with that, I finished. I thank you all. I hope I've not been too boring or too detailed, but of course, it's important to explain some, at least, concept so that we can all understand what we're talking about. Thank you very much.